Assalamualaikum and hi everyone. We are from section 1 group number 4. Today, our group will present the development of an S-band microstrip patch antenna designed specifically for 3U CubeSat applications. Our project is driven by the Malaysia Space Exploration 2030 MSE 2030 roadmap, which aims to enhance national capabilities in satellite technology. The primary challenge was to design an antenna that fits the strict SWAP size, weight, and power concept of a 3U CubeSat. We focus on a target frequency of 3.5 GHz with specific mission requirements, a gain of at least 3 dBi and a bandwidth of 80 MHz. To achieve this while keeping the design compact, we utilize a miniaturized patch design on a 1.6 mm FR4 substrate with an 80 x 80 mm footprint.
This project focused on the design of the CubeSat S-band communication antenna. CubeSat are extremely constrained by size, weight, and power, which make antenna design particularly challenging, especially at S-band, where higher gain is required for reliable telemetry, tracking, and commanding. From the literature, several antenna types have been used in CubeSat. Monopole and dipole antennas are simple and omnidirectional but suffer from very low gain and often require deployment mechanism. Helical antenna provide a better gain but are bulky and mechanically complex. Microstrip patch antenna, on the other hand, are low profile, lightweight, and can be directly integrated onto CubeSat surface. However, single patch elements typically have limited gain, so recent research trend moved toward patch array configuration. Key findings from the literature show that antenna miniaturization is mandatory. High permittivity substrates such as Rogers DMM10 have reduced physical size and array configuration essential to achieve the required gain within CubeSat surface constraint. Based on this finding, a miniaturized space array antenna was selected for this project. Based on the problem analysis and literature review, a mission-driven antenna specification was defined. The antenna is designed to operate in the S-band at 3.5 GHz with a maximum footprint of 80 by 80 millimeters, which comply with CubeSat surface limitation. The minimum required gain is 3 dB with a design target of 6 to 8 dB and a bandwidth of at least 80 MHz to support CubeSat TTC and C communication. A linear polarization is selected for simplicity, and Rogers DMM10 substrate is used to enable size reduction through its high dielectric constant. For BBL phase 1, an initial 2x2 miniaturized microstrip patch array is proposed. Slow loading is introduced on each space element to further reduce size, and a corporate microstrip feed network is used to ensure equal amplitude and phase excitation, resulting in broadside radiation. This design serves as a scalable foundation where the array can be expanded to a 4x4 configuration in future phase to achieve higher gain.
For antenna modeling and simulation, we're using the software and its HFSS. For our antenna dimension, the operating band is S-band. The frequency operating was in the middle of 2.5 to 3.5 GHz. For our PCB size, we choose the size of 60 x 60 mm. For the patch size, we choose 21 and 22 mm. For substrate, the constant of the substrate is 4.4 and the material was epoxy. The thickness of the substrate after we optimize is we choose 1.6 mm. So the precision of the patch, we have the cutting of 10 mm times 5 mm. The microstrip fits. The microstrip fits measurement is 5 mm to 3 mm from the patch until to the ports of the antenna. Graph shown is the return loss graph or S11 graph that we got after we simulate our design in ANI's HFSS. So the graph shows the frequency range between 1.3 to 2.4 GHz for the frequency. As the dimensions are adjusted, the resonance behavior shift along the frequency axis, which we confirm that the antenna resonance is highly sensitive to the parameter, geometric parameter. Although the return loss is shallow and don't reach negative don't reach negative 10 dB decibels, the trend shows the correct resonance behavior and validates the antenna models. So the results is further optimized of the patch dimension and fit structure is required, which is addressed in the next optimization stage. So for the next optimization stage is we fabricate the patch antenna and we're gonna test it using the network analyzer.
So the fabrication methodology we have two, which is we have our objective and material. So the objective is to convert optimized simulation design into a physical prototype compatible with a 3U CubeSat standard. And then for the material, we are using a rigid FR4 explosive glass substrate, which is the thickness is 1.6 mm and copper cladding is 35 micrometer. So the fabrication workflow, we have 5, which is for the first one, we have a surface preparation. So we're using a mechanical cleaning using the RBM 300 brushing machine to remove the oxidation and impurities. And the second one is lamination, the application of photosynthesis dry film onto the copper surface. And then the third is the pattern transfer, which is UV exposure. So we are using the Vanguard Helix UV unit to transfer the circuit pattern from transparency film to the board. And then for the fourth one, we have chemical etching because we are using the Vanguard spray etching machine to remove unwanted copper and reveal the antenna geometry. And for the last one is assembly. The stripping remaining photoresist, drilling the feed point and soldering the SMA connector.
Next, moving into the fabrication phase, we transition our optimized design into a physical prototype using PCB milling. I would like to highlight the physical specification of the fabricated unit. First, the substrate size was measured at 60 mm by 60 mm. This is a critical success as it will clear the maximum allowable limit at 80 mm by 80 mm set for the CubeSat mission, ensuring easy integration. For the patch geometry, the final dimensions came out to exactly 21 mm in length and 22 mm in width. This perfectly matched our optimized simulation parameters, which is vital for maintaining the target 3.5 GHz resonant frequency. Regarding the etching quality, a visual inspection confirmed clean copper traces. We observed no sign of over-etching or bridging, which preserved the impedance of the feed line. Finally, our connectivity. We successfully soldered the SMA female enlarged connector to both the feed line and the ground plane. The connection is mechanically stable and secure, meaning the prototype is now fully operational and ready for the VNA measurement and validation phase. To conclude, this project successfully navigated the full engineering life cycle from the initial literature review to physical validation. Our laboratory measurement in PBL6 confirmed that the antenna is mission ready. While we observe a minor frequency shift to 4.02 GHz due to substrate tolerance, our return loss of negative 6.43 dB and VSWR of 2.8 demonstrate excellent impedance matching. Most importantly, our measured gain of 5.0 dBi far exceed the minimum requirement of 3 dBi. This result proved that our antenna is fully compliant with MISA requirements and is ready for integration into a 3U CubeSat structure. For future work, we recommend exploring high-frequency laminates like Rogers to further minimize loss. Thank you.